and nonpolar compounds. So a polar covalent bond forms when there's an unequal sharing of electrons. And this is when the two atoms that are sharing the pairs of electrons have different electronegativities. So on our scale, we're going to have nonpolar covalent from 0 to 0.4. And that's where there's an equal distribution of electrons in the overlapping orbital. So if like this is two oxygen atoms sharing electrons, they have a double bond because they're sharing two pairs of electrons, then those 8 electrons are spending equal amount of times in each of the p orbitals that overlap for those two oxygen atoms. Okay. Then in polar covalents are 0.4 to 1.7. So there's an unequal distribution. So for example, like as in hydrogen fluoride, we said this was hydrogen, this was fluorine. Hydrogen is sharing its 1 electron and fluorine is sharing those 7. Well, this is very highly electronegative, and most of those electrons that are bonded are spending more time in that p orbital of fluorine than in the s orbital of hydrogen. And that's why you have an unequal distribution. Therefore, you have this more positive nucleus is exposed, and you have more of an electronegative shell here, so it's polar, so positive, negative, polar. Then for 1.7 to 4.0, they have completely separate orbitals, like as in sodium and chloride, where sodium loses 1 to have an octet, but comes a +1, and chlorine gains it to have an octet, becomes a -1, and so you have an oppositely charged, which forms a neutral compound, +1 -1 equals 0, but they're completely separate orbitals, and that is ionic. So between a metal and a nonmetal, 2 nonmetals. Okay. In this region, you can have things that are strongly polar covalent, but be in that ionic range. So you have to look at what they're made of to know. Plus, you can also use your trends and electronegativity values, which we went over earlier, and I'll show you those here momentarily. Likewise, if you have something that's 1.6 and is a metal and a nonmetal, it's weakly ionic. Okay, so you can have things in this 1.7 to 2.0 that are strongly polar covalent, or you can have weakly ionic. So you have to look at what they're made of in order to determine exactly what they are. So you don't have to memorize these numbers, but if you'll recall, the general trend is as you increase across the periodic table, electronegativity values increase. So the highest electronegativity values are found here. Notice it's 0 for the noble gases. And as you go down the group, electronegativity values decrease. So the lowest values are down around here, around cesium, francium, and radium. Okay, and then as you go down, also with the rest of the periodic table, they decrease. All right, so just knowing that if I bond something with this, it's going to be polar covalent. Or if I bond something with this, it's going to be ionic. Or if I bond these two together, it's going to be probably nonpolar covalent because there's not much difference between their electronegativity values. Okay? So let's look at hydrogen fluoride. So hydrogen has an electronegativity value of 2.1 and fluoride 4.0, so 1.9 is very polar covalent. So again, if we look at that 1.9 value, since it is 2 nonmetals, it falls in that little range. Again, hydrogen and fluorine have very different electronegativity values, so very low electronegativity, high electronegativity, so it is very strongly polar covalent. But if we compared hydrogen iodide, though, and its electronegativity values, our difference is a 0.4. Okay, so again, hydrogen and iodine, which is way down here, notice they decrease greatly. Notice the 2.1, 2.8, and it's even less for iodine, which is down here. So very little electronegativity variance, and it falls right on the line, so you can either call it, polar covalent or non-polar covalent, but it's very weakly polar covalent, or it's just non-polar covalent. Or if we look at sodium chloride, which has a 2.1 difference, and its electronegativity makes it ionic. So it's over here, sodium and chloride. Very big difference. Again, a metal and a nonmetal forms ionic compounds. Okay? So again, electronegativity trend tells us that the electronegativity values increase across a period and decrease down the group because nonmetals have very highly held valence electrons. Metals have very loosely held valence electrons. They like to form ions that are cations. These like to gain them to form anions. As a result, you can form ionic compounds this way, or if they share, especially anything with hydrogen in this tends to end up being almost a polar covalent most of the time, and the halogens for sure, oxygens for example, water is like the classic example of a polar covalent compound. Okay.